that oil spill down the coast is a real mess. Ugh, I must have washed 1,000 birds. And they were all so pitiful.
You know, you look a little like a dirty bird yourself. Why don't you go wash up while I finish making the hot peppermint tea? When you're cleaned up, let's watch those movies if you want to. The ones of the vacation trip we had last summer.
Okay. I like peppermint all right. Just as soon as I get all this slime off of me. Ugh. Oh no, my new gold ring.
Oh, what's the matter?
It just went down the drain and all this water rushed right in after it.
Oh, I'm sorry. Listen, don't worry, because sinks are equipped with traps. They're just made for people like you who drop their rings down the drains, okay? Don't worry, we're gonna get it back for you in just a minute.
Yeah, but wouldn't the water just push the ring right through the trap and down to the sewer? On last night's news, they had a story about where the sewage plant has a whole collection of false teeth and babies' toys that got flushed down the toilet.
Well, most toilets don't have traps, but sinks do. Okay, now you put the bowl up underneath the trap to catch the water.
Okay.
And I'll unscrew these plastic collars that hold the pipe in place. We have to unscrew both of them, and that should release the trap. And if we're lucky, it should get your ring back.
Okay.
Here's the trap. Let's see what we have in here. Oh.
Voila! Oh, you did it! You saved my ring. But how did you know that it didn't just go right down to the sewer?
Well, I figured that it would be trapped by its own high density. You see, the metal in the ring is much higher density than the water that washed over it. So it just kind of shifted to the bottom of the trap, kind of like a rock settles on the bottom of a pond. But if it had been plastic, you know, it would have washed all the way to the sewer, just like all those baby toys.
Density is the ratio of the mass of an object to its volume. The gold ring has a density of 15 grams per cubic centimeter. A plastic ring has a density of 1.5 grams per cubic centimeter. And water has a density of 1 gram per cubic centimeter. Since the rings have more mass per volume than the water, we can say the rings are more dense than water. We can also say that the gold ring is more dense than the plastic ring. Even though both rings are more dense than water, and both rings sink in water, they do not behave the same way if they fall into the plumbing. Watch as the gold ring falls into the plumbing and water runs over it. The gold ring is 15 times as dense as the water, so it can't push the ring out of the trap. Now watch the plastic ring. The plastic ring is only 1 1/2 times the density of water. When the water runs over it, the plastic ring bounces along with the water, out of the trap and on through the plumbing. By running water over the rings in the plumbing trap, we could actually see that the gold ring is more dense than the plastic ring. We found that both rings sank in water because they are both more dense than water. But the gold ring stayed in the plumbing because it is much more dense than the plastic ring that washed away.
Do you suppose that density is the reason the oil was floating on top of the ocean today, getting all the birds yucky?
Probably. Last time I was here, you shook the salad dressing to mix it up. Surely you remember what happened when you put it down again.
Yeah, it's separated. Now see, this one my Aunt Nancy shook up earlier for her lunch, and it's already separated. Gosh, just look at the difference.
That's density for you. The same material will float or sink the same way. Even when you mix it up, it's separated again, just like your aunt's salad dressing.
You know what would really clean up the ocean? A humongous gravy skimmer.
You're right, but I don't think they make one big enough. So it's a good thing we were there to rescue the birds. Gosh, look what time it is. I told Mom I would be home in time for dinner. I'll see you later.
Bye. Gosh, I guess I better get Aunt Nancy's shirt off before she comes home. Get mine out of the dryer.
Oh, I just love home movies.
Yuck. I look so gross in that suit. How could you possibly take a picture of me like that?
Oh, Joni. Oh, I was self-conscious when I was a teenager, too, I guess. You'll outgrow that.
But first, Aunt Nance, you have to prove to me that the density of water really changes how things float.
Okay. Here's some shots of your friends when they were practicing on their scuba diving. Remember when Alice was practicing in the swimming pool? See how easily she sinks there?
Yeah, so what's the big deal?
Well, the big deal is that she's in the ocean here. And now, see, she can't seem to sink. That's why Keith has to give her some metal weights. He gave her 5 pounds of metal weights. You see, the ocean water is more dense than the swimming pool water, so she needs more weight to make her dense enough to sink to the bottom.
That's it? 5 pounds and she sinks?
Well, remember that 5 pounds was 5 pounds of metal weight, and metal is much more dense than water. Well, Alice could have gained 5 pounds of fat, but that 5 pounds would only have made her float better, because fat is less dense than water. So it matters what that extra 5 pounds is made of.
That's really neat. Is it just the salt in the ocean that makes the water more dense than regular water?
Well, it's mostly salt, but there are a lot of other minerals dissolved in the ocean. Do you know that the ocean would be even more dense if it were filled with sugar water? Because water can dissolve more sugar than it can salt.
Yeah, and if the ocean were made of sugar water, we could cook with it and make all sorts of yummy desserts.
Then you really would get fat.
Oh, but it'd be worth it.
Oh, and think how many extra weights Alice would have to have in order to make her sink in an even more dense ocean. Oh, come on, I've got some more things I want to show you. Let's go to the kitchen.
Differences in density are the reason some things float and others sink in the same environment. Slight changes in the environment or the object can affect whether an object floats or sinks, or even the height at which it floats.
Honey, would you please get me some ice cubes out of the freezer?
Sure. Are these the cubes you wanted?
Yes, thanks.
Why are they colored?
All the better for you to see them, my dear. Okay, now watch this. I'm going to pour water into this glass and some isopropyl rubbing alcohol into this glass. And we're going to have to make real sure that we clean up carefully afterwards, because rubbing alcohol is really bad for you, and we wouldn't want to drink any by accident. Okay, now drop one of your ice cubes into the water.
Okay, but everybody knows that ice cubes float in water.
Right. Now drop one into the rubbing alcohol.
It sank! How did you do that?
It wasn't me, it was the rubbing alcohol. You see, the ice cube is less dense than the water, but more dense than the rubbing alcohol.
I sure hope nobody ever fills a swimming pool full of rubbing alcohol. If the ice cube couldn't float in it, I probably couldn't either.
You're right. Now do you believe me about the ocean and that you're not fat?
No. What do you think would happen if I poured this glass into that glass?
Let's try it. Maybe a mess.
Hey, look at this! I poured the water into the isopropyl alcohol, and now it's floating in the middle.
Oh, that's great. You know what you did? You made the surrounding liquid the same density as the ice cube.
I have other uses for ice.
Hey, now, none of that stuff. I think I have another tape on ice that you might be interested in seeing.
When things don't mix, like the ring and the water flowing down the pipe, or the fat and the gravy in the gravy skimmer, it's easy to see which substance is more dense. The more dense substance sinks to the bottom. But when the two substances do mix, like rubbing alcohol and water, then you need a third object to help you compare the densities. In this case, the third object was the ice cube. The ice floated in the water, so we knew the water was more dense than the ice. The ice sank in the rubbing alcohol, so we knew the ice was more dense than the rubbing alcohol. This gives us a ranking. Most dense is the water, because the ice floated in it. Next dense is the ice, which floated in water, but sank in rubbing alcohol. The density of ice is between that of water and rubbing alcohol. And least dense is the rubbing alcohol, where the ice sank. When Joni mixed the rubbing alcohol and the water, the ice cube became suspended in the middle. What did that mean? It meant the ice and the surrounding mixture were the same density. By mixing the high-density water and the low-density rubbing alcohol, the mixture became the same density as the ice.
You know, Aunt Nance, you have got to be the weirdest aunt in the entire world. I mean, where did you get these tapes on rocks? Phase changes?
Oh, so I collect weird tapes. You know, you should consider yourself lucky. I could collect things like lizards.
But that would be really neat. Here's that tape about ice that you wanted me to find.
Okay, put it in the VCR. Let's see what happens.
This pool is so hot, an alligator would be happy in it.
I've heard of heaters for pools, but I've never heard of a cooler. Let's see if the ice cream truck has ice to cool the pool. I'll go with you. I'll get the wagon.
That was huge. Well, one of you help me lift it? Yeah, I bet it sinks to the bottom.
Hey, it popped back up. There'll be more fun to play with that way.
Let's put the other one in.
An iceberg coming to get you. It's so heavy, I wonder why it doesn't sink.
Heaviness is not the same as density. If you think about it, a big enough piece of any substance would be heavy. Even something as light as dust could weigh a ton if you had enough of it. So heaviness alone isn't enough to make an object sink. Another factor has to be considered: volume. If you divide the mass of an object by its volume, you can calculate its density. Density is what determines if an object will sink in water. Remember the riddle, which weighs more, a pound of bricks or a pound of feathers? As you can see by the words, there is a pound of each substance, so of course they weigh the same, but only the bricks will sink in water. Here we have a block of ice and a piece of metal, each of which have a mass of 4.54 kilograms, which at Earth's gravity have a weight of 4.54 newtons or 10 pounds. We drop both of them into the swimming pool. As you can see, the metal is much smaller than the ice, and it sinks to the bottom of the pool, showing that it is more dense than the water. The ice floats, showing that it is less dense than the water. No matter how big and heavy a piece of ice we can get, the ice will still have the same density as this piece, and will still float. A bigger piece of any substance will be heavier than a small one. That's why you have to divide the mass of an object by its volume to find its density. Only density determines if an object will sink in water.
How many people did you say were coming to your party tonight?
About 15 or so. But I'm not sure if Andy can come because he may have to babysit his little brother.
Oh, say, turn channel 16 on. It's almost time for Nova.
Okay.
Are you tired of seeing your salad dressing separate, your mayonnaise clump, and your smoothies turn out chunky? What you need is our Blender Chef. To demonstrate how well it works, we'll mix together colored lamp oil and water. First, watch. They don't mix under normal circumstances. The oil is poured onto the water. It floats right on top because it's less dense than water. Now watch again as water is poured on top of the oil. The oil rises to the top, showing again that not only is it less dense than the water, it doesn't mix with the water, no matter what order the ingredients are poured into the blender. Now watch, as a blender jar containing both colored lamp oil and water is whirled for 3 seconds at full speed. The oil has broken into tiny droplets and dispersed throughout the water. Blender Chef has done it again, ladies and gentlemen. It's done the impossible by mixing water and oil. Well, they were mixed. You can't fight density forever, you know.
Blender Chef, the blender that can do almost anything.
You know, that commercial reminds me of the time Alice and I were fooling around in the kitchen with our hot water lava machine. Didn't you just get the video camera around that time? Do you still have the tape?
Of course, I would never throw away such a good example of the effects of temperature on the density of a liquid.
Come on, Aunt Nance, you are not going to tell me that everything fun depends on density.
Well, why don't I play the tape for you? And then you can decide if it uses density to your satisfaction.
She is going to make me think that everything fun depends on density.
I know a magic trick.
Elizabeth, everybody knows that one.
What am I going to do then?
Well, you filled this bottle all the way up to the top with water, and now you're going to put that piece of cardboard over the mouth so that you can turn it upside down, which will show that if air can't get in the bottle, water can't get out. Ta-da! Okay, it looks neat the first few times you do it, but I've seen it before.
But that's not all there is to it, Joni. Well, then show me something new, Elizabeth. Okay, now watch. When I put it on top of the red one, it's gonna mix a little. Okay, are you watching?
I'm watching.
Watch careful.
I'm still watching.
I'm gonna pull the cardboard out.
I'm still watching.
Okay, we'll keep watching.
I'm watching, Elizabeth, and there's not a whole lot happening here.
Well, I have another bottle of water I heated in the microwave. You watch that.
Be careful you don't spill it.
I'm not a baby, you know.
Elizabeth, I just said that because the water is hot, okay?
Okay. Well, here I come. Okay. Place this here. Now, Joni, watch what happens when the water is hot.
Just like the cool water, it's going to mix with the clear water. And you're going to gradually have diffusion. Big deal.
Okay, smarty pants. Well, then you pull the cardboard out, and then we'll see how my trick works. Got it?
I think so. Oh, wow, that's really neat. It looks just like the lava lamp at the art museum. You know, the one where the lamp heats the lava and all the lava rises to the top?
Mm-hmm.
Pretty cool. Okay, I guess your magic trick is pretty neat after all.
Thanks.
It's a pretty good trick. But there's no magic involved, I know that. So how does it work?
Density.
You have got to come up with a better explanation besides that one little word for the wonders of the world.
No, really, it is density, Joni. Look, the density of liquids changes with heat. Hot water is less dense than cold water. So when the cardboard was removed and the hot water was on the bottom and the cold water was on the top, they began to exchange places. And since the hot water was colored, you were able to actually watch the hot water rise to the top, just like the oil rose to the top in that blender commercial.
I see. I'll have to show Dad that one. He actually likes science when it's neat.
Come on, let's go to the kitchen. I have one more thing I want to show you.
Okay.
Guess what I did today, Joni?
What'd you do, Aunt Nance?
I made a density gradient using my flower vase.
Sounds like something out of a horror movie. Oh, and it stinks.
Oh, so it smells a little. A density gradient is a quick way to separate a lot of things by density, all in one fell swoop.
Like all this junk in your drawer?
Sure, we can use that. Here, let me show you how I made it. I started by pouring some ordinary tap water in. That's the most dense liquid I have around the house. And then I added some mineral oil. The mineral oil doesn't mix with the water, and it floats on top, just like the salad oil.
It's looking slimy, Aunt Nance.
And last, I poured in some rubbing alcohol. Now, I don't want the rubbing alcohol to run right through that mineral oil and mix with the water, so I'm going to pour it in very slowly using this knife.
That was neat. Did you see how the mineral oil bubble popped back up in there?
Uh-huh. Now, see, the rubbing alcohol doesn't mix with the mineral oil, and it's less dense than the mineral oil, so it floats on top of everything. And the mineral oil in the middle keeps the water from mixing with the rubbing alcohol, so we get 3 separate layers for our density gradient. I wonder what one of those ice cubes would do in this density gradient.
Well, I remember that ice floats in water and it sinks in rubbing alcohol. So would it end up in the mineral oil?
Why don't you drop one in and see?
Okay. In the mineral oil. That's really neat.
Yeah, it's
Let's
floating
try
on
some
the
of this
water.
other stuff.
How about the popsicle stick first? I want to see if it floats on any liquid less dense than water.
One popsicle stick entering gradient.
Floating on the rubbing alcohol.
Okay, and this wax paper from last night's dinner. Only people like you keep wax paper from the night before, Aunt Nance. Staying in the rubbing alcohol.
How about that?
One washer.
Now, that's dense.
That's dense. And candle from last year's birthday. Down
Down, down, down into the mineral oil, ladies and gentlemen. It's floating. No, it's sinking. There it goes. It's down, and it's...
It's more dense than the mineral oil. But less dense than the water.
Yes. And seashell from last summer.
Very dense. Look at it go. Now we know all the relative density of all of these objects, and we didn't even have to weigh or measure any of them.
Yeah, but Aunt Nance, now you have a huge mess to clean up.
Oh, yeah. Well, speaking of messes, I did promise you some cocoa and marshmallows, so why don't you help yourself over there? Pretty nice hot water dispenser there, huh? It saves a lot of time.
Sure does. Oh, yummy hot cocoa. Aunt Nance, don't tell me.
Thanks. Don't tell you what?
You know.
No, I don't. Oh, unless you mean you want me to give you a note from your teacher so that you don't have to go to school tomorrow and you can go wash some more birdies. Well, that's between you and your parents, dear.
Actually, I thought you were going to ask me to figure out which was more dense, the marshmallows or the cocoa.
Now, would I do something like that?
Joni and her Aunt Nancy discovered many important ways in which you can see density at work every day. As Joni guessed, density is responsible for many of the ways we enjoy the world. The world around us is made up of solids, liquids, and gases. Each solid, liquid, and gas has its own density. Liquids provide a good medium in which to test the density of solids and of other liquids. Differences in density explain why salad dressings separate, ice cubes float in water, and seashells sink to the bottom of the ocean. The density of liquids can be detected in many different ways. Less dense liquids float on more dense liquids. For example, oil floats on vinegar because oil is less dense than vinegar. If one liquid is floating on top of another, you can tell which one is less dense. The less dense liquid is always on the top. When liquids of different densities mix, the mixture has a density in between that of the starting liquids. An ice cube floats in water because it is less dense than water. An ice cube sinks in rubbing alcohol because it is more dense than rubbing alcohol. But when water and rubbing alcohol are mixed, the ice cube becomes suspended in the middle. This shows that the mixture of water and rubbing alcohol has the same density as the ice, a density between that of water and rubbing alcohol. If more material is dissolved in a liquid, then the liquid becomes more dense. Temperature can affect density too. If the temperature of a liquid increases, then the density of the liquid decreases. Alice's trick with the water in the bottles worked because hot water is less dense than cold water. When Alice placed the bottle of cold water on top of the bottle of hot water, the hot water rose up through the cold water to the top bottle. The less dense hot water actually traded places with the more dense cold water. Density is different from weight and size. A big heavy ice cube is still ice, and it still floats, just like a tiny ice cube in a glass of water. Any two substances that have the same density will sink or float the same way, no matter whether you have a big piece of it or a little one. Density is a combination of two properties of an object. To find the density of an object, you have to know both its volume, how much space it takes up, and its mass, which can be measured in grams. Density is the mass of an object divided by its volume. Here we have a graduated cylinder sitting on a balance. A graduated cylinder is like a measuring cup. As honey is poured into the graduated cylinder, you can read the volume of the honey by the lines on the glass. You can read the mass of the honey from the numbers on the balance at the right of the screen. The volume of honey here is 18 milliliters, and the mass is 26.4 grams. The density, then, is 26.4 grams divided by 18 milliliters, or about 1.47 grams per milliliter. Since water has a density of 1 gram per milliliter, this means honey is almost 1 1/2 times the density of water. You can use density to your advantage. A gravy skimmer with the spout on the bottom lets you pour the more dense broth away from the less dense fat by pouring the broth from underneath the fat. The very high density of jewelry keeps it from washing away down the pipes with the less dense water. The density of different liquids is responsible for much of their behavior at the beach, in the kitchen, or wherever we may find them. Density is why a heavy block of ice can float, while a tiny metal washer sinks. Density explains why salad dressings separate and why gravy skimmers work. Density is an aspect of the world that is invisible until we know what to look for. Once we understand it, many new patterns appear.